Okay, I guess maybe we can start. So welcome to 130B, Quantum Mechanics. Today we are going to continue our discussion of hydrogen atom and hopefully finish this section. So last time we have been starting to talk about hydrogen atom, which is describes electron moving around the proton. So we start from the classical mechanical description where the system is described by a Hamiltonian. And the Hamiltonian operator corresponds to the energy of the system, which contains the kinetic energy and the potential energy. Kinetic energy has to do with momentum squared over twice of mass, and this potential energy is like 1 over r, which is the potential of a Coulomb potential that the electron experiences in the potential of a proton. So we have made some simplification by rescaling the position and momentum, and then we end up with a simplified Hamiltonian, which does not depend on the mass or the coupling constant. So we basically wish to solve this problem. This is a quantum mechanical problem. In quantum mechanics, we should replace all these P and R by their operator correspondence. But in classical mechanics, it already gives us some intuition. If we write down the equation of motion, from that equation of motion, we can verify that there are angular momentum that is conserved, which is r cross p, which is the angular momentum. And it is related to the three-dimensional rotation symmetry in the system, because if you rotate with respect to the proton, the system actually, the Hamiltonian looks the same. But there is an unexpected conservation law, which is the LR-L vector, Laplace-Runge-Lenz vector, which is defined as P cross L minus R over R vector over R amplitude. So this vector actually characterizes, first of all, its direction characterizes the direction of the major axis of the orbit, and then the amplitude actually is the eccentricity, is how what's the shape of this orbit. And then if you try to verify it on the classical mechanics level, one can also show that this quantity is also conserved. So there are more than what we think should be the conserved quantity. Both angular momentum and the LR-L vector are conserved. Angular momentum basically specifies what is the orbiting plane, because angular momentum is always perpendicular to the plane of the orbit. But this LR-L vector further specifies within this orbiting plane where is the major axis, and that axis direction also not changing with respect to time. And what is the shape of the orbit? It basically determines that. So because of this, the angular momentum and this LR-L vector are always perpendicular to each other, because angular momentum perpendicular to the plane, but LR-L vector is always lies within the plane. So that's why their dot product is always 0. Not only that, we also want to know, for example, how is the energy determined by these two conserved quantities. Because once we know what is the angular momentum and what is the LR-L vector, we basically can determine the orbit. We can fully draw what's the orbit, what's the shape of it. And once we know what's the orbit, we can evaluate the energy associated with this orbit, right? So there must be a third relation, which is, another relation, which tells you how energy is related to L and A. And that equation, I think, is down there. We will talk about that. So basically, last time we promote everything to quantum operators, the Hamiltonian, the angular momentum, and the LR-L vector. You can see all of them are operator now. And there is also a relation between L and A. One relation is that their dot product is 0 because they are orthogonal to each other as vectors. And then there's also another relation which tells you how this Hamiltonian is related to L and A. So all the algebraic relations are here. So that's what I talk about. First of all, A and L, their dot product is 0, meaning that these two vectors are perpendicular. And then the second equation tells us how does the Hamiltonian related to L and A. So as long as we know how to solve for eigenstates of L and A, pretty much we can express the energy eigenstate in terms of eigenstate of L and A. And we can calculate the eigenenergy in that way. So that's basically the idea. But in order to solve for that, we need to go through all the algebraic relations. That's what we learned about in the quantum bootstrap. So we need to start from the very basic algebraic relation, which is the commutator between position and momentum. And then from that, we can prove the following commutation relations. Of course, admittedly, it's not very easy to check, but I wrote a program to help you check that. And the physical meaning of this commutation relation, basically the first two says that Hamiltonian commute with each component of the L vector and the A vector. Of course, each component in quantum mechanics is also an operator, but it just basically means that the angular momentum and the LR, L vector are all conserved quantities, because in quantum mechanics, any observable that commutes with the Hamiltonian will not evolve in time according to the Heisenberg equation. And then there's also some relation that is the interrelation or among L and A vector components, basically. And then we can see the L components, basically, their commutation relation is like an angular momentum as expected. But the A, this vector, does not behave like an angular momentum, but it almost behaves like some kind of angular momentum up to this nasty H. So somehow people come up with the strategy that if L and A are conserved quantities, then we can basically focus on an energy subspace, eigenenergy subspace. That means focus on an energy level, because within each energy level, there are still degeneracies. There can be multiple states that has the same energy. So it's still non-trivial. We want to understand what are those states. But for those states, because they share the same eigenenergy, so we can treat within that space, this Hamiltonian can be simplified and be treated as a constant. So for that, we can basically simplify this algebraic relation by assuming that if we are focusing on those bound states with energy less than 0, bound state meaning that the electron will be bound to the proton without flying away, and then the energy will be less than 0 because we assume that infinite far away from the proton that energy is considered to be 0, then if you are close to the proton, then the energy is lower, which is less than 0. Okay, so suppose we fix such an energy eigenvalue, assuming that there exists such an energy level, then within that energy level, or within that subspace, eigenspace of Hamiltonian basically gets replaced by a constant E. And then we can renormalize this A vector by 1 over square root minus 2E. That is just for convenience, because once we do all this normalization, it turns out that the N and N, in terms of this N operator, its commutation relation has a very simple form. Remember, previously we have some H over there, but now H gets replaced by E and further gets renormalized and absorbed into the definition of N, such that we have such a clean relation between all the commutation relation between the angular momentum and this N is, you can say it is like a rescaled LRL vector, okay? And then these relations looks very similar, and then we also inherit the two relations. L and N are still orthogonal to each other, just as L and A are orthogonal to each other previously. And then there's a relation that tells you if I know what is L, what is N, and how do I compute the energy. So this tells you how energy is related to the quantum numbers given by these L and N. But if you look at this commutation relation, for L, it's very nice. It follows the angular momentum commutation relation. We always want to transform the unknown problem into our known problem. So we know how to solve angular momentum problem. We know what are the quantum numbers and associated states. But for this N and N, the commutator goes to L, and L and N commutation goes to N. It's something, there's a mixing between L and N. So that's why people further think about it and then figure out, okay, in fact, if you can try to recombine these two operators in such a way that basically T and S are just a linear combination of L and N with a plus combination or a minus combination. So if you viewed, so basically L is like a vector which is perpendicular to the orbiting plane, and n is a vector which lies in the plane. And then L plus n is almost like something like that. This is like L plus n. Maybe divide by 2, then it's half of the size. And then this L minus n is the other one, L minus n. So if you start from a perpendicular frame of coordinates and then try to add these two vectors together or subtract these two vectors together, one is called, I think one is called T. This is T, this is S, right? So one immediate conclusion is that T squared and S squared must be the same, which is down there. These two vectors must have the same length if they are just linear combination, plus and minus linear combination of the perpendicular vectors. That is simple geometry. And then there's also other very nice property that it turns out that these T components, their commutation looks like angular momentum. And for S, that also independently, S also has 3 components. It also forms angular momentum. And T and S, now they commute with each other. That means these T, we have 3 T operators, 3 S operators. They are independent. So that's why we can treat the system as as if there are 2 angular momentums. There are 2 independent SU2 groups. And then these T and S are exactly the T and S we encountered in homework 4, where we show that when we talk about SO4 rotation, which corresponds to a rotation in a 4-dimensional real space, and then SO4 is any rotation that preserves the length of a real vector in a 4-dimensional space. So that rotation can always be generated by 4x4 matrices, where the 4x4 matrices is purely imaginary and anti-symmetric. And then in homework 4, we show examples of how T and S can be written down in terms of these anti-symmetric, purely imaginary matrices. And then from there, you can actually show that indeed these generators of SO4 satisfy this commutation relation. So we should think that this commutation relation as the defining property of the SO4 group, basically. Any operator, if you can find 2 sets of operators in your system, and these 2 sets of operators separately satisfy angular momentum commutation relation, and then they both commute with the Hamiltonian as a conserved quantity, then we say that the system must have a SU2 cross SU2 symmetry. But if you have 2 SU2, that's actually SO4, actually. So there's a relation between these groups. And then, so you may think that there are 2 independent angular momentum, some very abstract angular momentum in the system, and it is not purely independent. It's almost independent, but up to a constraint that T squared and S squared must be the same. We will see it's very important in the later discussion that because if you think about the first angular momentum system, it has the J quantum number and M quantum number, and the second one also have its J and M. But this relation basically lock their J quantum number together because these 2 angular momentum, their square must be, their Kashmir operator must be the same. So this is a constraint imposed to the system. And then we can also simplify the other condition, which tells us how the energy is related to this T angular momentum. So this T actually purely determines what the energy should be. So now, given that T and S are 2 angular momentum-like operators subject to a constraint T squared equals S squared, so we can write down the eigenstates of T and S labeled by certain common eigenstate of these operators labeled by the quantum numbers. So I should label by T and MT. That's like the J and M for T. And then J and M for S, which may be called S and MS. But because this J quantum number, the angular quantum number of T and S, they are the same, so I just use a single T to denote the angular quantum number of T and S. The magnetic quantum number for T and S will be separate. So that's why the state will be jointly labeled by 3 quantum numbers. One is T, the other is MT, mt will be ranging from minus t to t, and then there's a ms. Ms will be ranging also from minus t to t. And then this t as an angular momentum quantum number, it will take values like 0, 1 half, 1, and so on, all the integers and half integers, such that on this kind of state, if you apply the t square and s square operator, because they are actually the same, they both give you the t times t plus 1, which is what we know as a Kashmir operator acting on the angular momentum eigenstates. And then if you apply the t3 operator, it's also, this state is also eigenstate of t3 with eigenvalue mt. And then this state is also eigenstate of s3 with eigenvalue ms. So these are the meaning of these three quantum numbers. They are the quantum number that specify the eigenvalues of t square, s square, and t3 and s3. Okay. So for each fixed t, basically there are how many degeneracies you can count, because mt can range from minus t to t, and then ms can also range from that. So for mt, there are 2t plus 1 states. But for ms, there are also 2t plus 1 states. So altogether, there are 2t plus 1 squared degenerate states. So the degeneracy is actually pretty high. Yeah. Okay, so that's the solution of hydrogen atom. We have already solved the problem, and these are the eigenstates. And you may wonder how is that anyway related to hydrogen atom spectrum that we previously learned, maybe in the quantum mechanics, in the previous quantum mechanics classes. So now let's try to build the connection. So first of all, using the relation where the energy is related to t square, we can actually show that t square, that's just another way of writing it. And then because we know that t square, when it acts on those eigenstates, on these states, it basically takes the eigenvalue t times t plus 1. That means this state will have an energy, which is the energy E, such that it is related to t times t plus 1 in this way. So now what we need to do is to try to solve the energy. So we can rewrite, from this equation, we can rewrite energy in terms of this quantum number t. And we can see that the energy only depends on the quantum number t. It doesn't depend on mt, it doesn't depend on ms, because in the formula, what happens there, what appears in the formula is only t square, this operator. So you only pick out the eigenvalue that is associated with t times t plus 1. So after a few steps of simplification, one can show that the energy actually goes like 1 over basically this expression. So for this expression, we can see it has 1 over 2 times something squared. Something is 2t plus 1. 2t plus 1 actually has a nice property, because t goes like all the integers and half integers that ranging from 0 to all the way to infinity. So 2t plus 1, meaning that you first double it and then shift by 1. So when you first double it, it becomes 0, 1, 2, 3, 4, and so on. And then you shift it by 1. Add 1 to that, it becomes 1, 2, 3, 4, really. This originally start from 0, now start from 1. So now we can define a new quantum number, which is just a rewriting of this t quantum number, which is called n equals 2t plus 1, such that I can label my energy level by minus 1 over 2n squared. So this n quantum number is really the principal quantum number that we previously learned hopefully you have learned that in hydrogen atom. We know when electrons circulating around the nucleus, it has shells. Atomic structure has different shells, and different shell basically is labeled by different this n. N equals 0 is the first shell, second shell, third shell, and so on. So this n, the fact that this n quantum number, so-called the principal quantum number, must be an integer, actually follow from the fact that this t quantum number, which originated from some kind of angular momentum operator, must be must be either natural number or half integer. So these two facts are related. So by this derivation, we actually find what should be the energy eigen energy or the energy level of hydrogen atoms. So we can also restore the energy unit. Remember, we have done some kind of rescaling to simplify the problem, so we are actually solving a simpler problem. But by doing the rescaling, we can get rid of the mass of the electron and also this force constant, alpha, which is also called the fine structure constant, which characterizes what's the strength of the Coulomb interaction. So we can try to restore those units because previously we have divided our Hamiltonian by this unit to make it dimensionless. So now if you want to restore the dimension, you just multiply these units. So this is actually, if you look up the textbook, any textbook, this is the formula basically of hydrogen atoms. So we have successively end up with the correct formula which describe the energy levels of a hydrogen atom. So within this energy level, the corresponding eigenstate will just be this state. The eigenstate doesn't change, it's still the eigenstate. And this eigenstate, well, this T quantum number will now be set by n in this way. And then we also have the freedom to choose MT and MS, which ranging from minus T to T. So the total level degeneracy is 2T plus 1 square, which is also n square. So we know that, for example, if in the first shell we have one degenerate state, in the second shell we actually has 4 different states. The 4 different states basically in nowadays language is called S wave and P wave. S wave has one state, P wave has 3 states. But it is still very abstract, right? Because for T, maybe one can accept that, okay, T is just another way of labeling this principal quantum number which eventually determines the energy. So the energy level will be determined by 1 over n squared. So it's okay. But what is the physical meaning of this MT and MS? It seems that originally they are just coming from some very abstract angular momentum, which we have lost track of their meaning in these very abstract vectors. So in order to make sense of that, it is good to basically start with the ground state. So if we think about the ground state, what is the ground state? So energy goes like that, right? So energy, notice that there's a minus sign there. So if n is very small, then this number over 2n squared will be very large, but with a minus sign will be very negative. So yes?
What is alpha again?
Alpha is the fine structure constant which appears in the potential energy V of R equals minus alpha over R. So I'm packing all the electrostatic constants, charge, and everything. Everything you just put it in alpha. So this alpha actually is something like 1 over 137. It's also called fine structure constant. It has a very nice number. But never mind. It's just you can just think of alpha as the strength of the Coulomb interaction, something like that. So of course, if the strength of Coulomb interaction is very strong, then the energy scale is also very large, right? And if the particle is very heavy, then because the strength determines the potential energy. And if the particle is also very heavy, then it also has a lot of kinetic energy. So energy scale somehow has to do with both of them. But anyway, we want to find the ground state, which is the most negative energy state, which corresponds to n equals 1 or t equals 0. But when t equals 0, MT and MS has only one choice because both MT and MS must range from minus t to t. And now t equals 0, and the only choice is both of them is 0. So the ground state actually is unique. And the unique ground state, the only ground state is 0, 0, 0. T, MT, and MS are all 0, denoted as the in atomic physics, it's called a 1s orbital. This 1 stands for the principal quantum number, stands for n equals 1. And then this s basically means, we will talk about that later. S is just a name that people give to those orbitals which has total angular momentum, which is total angular momentum 0. So how do we find the wave function associated with this 1s orbital? So previously, we say there's a state. There's a very abstract state. And the state in the real space has a wave function representation, and we wish to understand that. So the wave function associated to this one is actually given by the differential equation t squared acting on this state equals 0, because this state is defined by the fact that there's basically this t quantum number is 0, which means t squared operator acting on this state must vanish, but must annihilate the state. But this basically also means that because previously, let me remind you, this T actually has a relation with the Hamiltonian. So it basically means that the state has a, what we need to solve is basically take the Hamiltonian acting on the state. It's the same as T squared. It's an equivalent concept. And then substitute the eigenenergy there. So the equation we have to solve eventually is you put the Hamiltonian here, which is, remember, this P squared becomes the differential operator in the position basis. And then this m alpha squared over 2 is the eigenvalue that we calculated previously. So you can see the idea here is that previously we start from the conventional idea of solving quantum mechanical problem is you first write down the Hamiltonian and you write down the eigenequation and you try to solve the eigenequation in order to determine the eigenstate and the eigenvalue, right? But in our approach, we first use other ways to find the eigenvalue first. But we just don't know what's the eigenstate. So we need to write down the Hamiltonian and plug in the eigenvalue and try to recover the eigenstate. That's another way of thinking it. And solving for this eigenstate, you just need to do some, there's some solving. You can solve this. One can show that if you take the eigenstate to be something like e to the minus r over a, where r is the distance of the electron to the nucleus or to the proton. A is something called the Ball radius. A is a length unit basically, and this A, at the beginning, you just try. Let's say if we try to substitute this solution into this differential equation, right? At this point, we don't know what should be A. We just assume that maybe there's some A. And what we do, I actually didn't explain why we take this form. I can only say it is because people have solved this equation and then find the form for the ground state looks like that. So we can actually a strategy instead of trying to solve it, try to substitute this equation, this solution, this trial solution into this equation. And actually, we can show that this trial solution indeed is a solution that allows this equation to hold. And then we can also show that in order for this equation to hold, there's some constraint for A. And the constraint for A is that A must satisfy such an equation, which means A is 1 over m times alpha. Somehow, one can show that. In order to show that, I think there's an exercise you can look up for details. Idea is very simple, just substitute everything in, and then maybe you can use Mathematica to help you finish the calculation. Okay, so after all these exercise, eventually, also after calculating the normalization factor, we can by solving this differential equation, this is the only place we need to solve differential equation. It's always when we try to understand what is the wave function, we have to solve it. But otherwise, we can already determine the eigenvalue pretty much in an algebraic manner. But with that, we can actually show that the ground state of a hydrogen atom looks like this. So what does that mean? This wave function describes the probability amplitude of finding the electron surrounding the proton. So r is the coordinate of the electron with respect to the proton, and then e to the minus r over a basically means it depends on the distance between the electron and the proton. If this distance is very small, then this exponential is close to 1. But if this distance is very large, then this exponential factor, this exponent basically says that the wave function will decay exponentially away from the proton. So the electron will pretty much circle or concentrate it near the proton, and then it will have a tail that decays away from the proton. So this is the probability amplitude or the wave function, and actually the probability to find the electron near the proton is square of this probability amplitude. You should take this absolute value square, which is the probability. And you can see, because this probability, no matter probability or probability amplitude, no matter you square it or not, the only difference after squaring it is that e to the minus 2r over a, basically. So pretty much the probability is also concentrated within the radius, which is given by this a. And this A is also called the Bohr's radius. Bohr radius is actually a typical length scale which describes the size of the electron, because it's like the size of the the size of the hydrogen atom, because it's also the size of the electron cloud. We can see it from a probability cloud, and then it doesn't have a definite position or momentum. It's just described by a probability amplitude. And then this ground state actually has the energy which is given by minus alpha over 2a. As if the electron is orbiting around the proton in a circular orbital of radius a. Because if you try to, in classical mechanics, if you try to think this way, if an electron orbital proton with this radius, you can actually use classical mechanics to calculate its energy. You'll find this energy is exactly this one. But in quantum mechanics, we know this picture is actually not correct. This A is just a typical length scale, which tells you what's the typical decay length of this electron wave function. And there's no definite orbital in quantum mechanics. And this is what I mentioned already, which is the electron cloud idea, which is the probability actually determined by this norm square. So this is all so this is what I want to say about the ground state. So you can just plug in the differential equation and find the ground state wave function, even if we start from an approach which does not explicitly solve the differential equation. Given the ground state, we can also try to understand what are the excited states. Excited states are actually labeled by higher principal quantum numbers. The reason is that we know that energy only has to do with this n quantum number. So the ground state is n equals 1, and then the higher excited state corresponds to n equals 2, 3, and so on. So for these higher excited states, then basically that means the T quantum number that we previously described in this angular momentum kind of approach will take a value of 1/2 and 1 and so on. So the state of the same principal quantum numbers are all degenerate in energy, and they are described by this state vector and with all this choice of T, MT, and MS. And then they can be viewed as a system of combining two spins of the same angular momentum T. So that goes back to the angular momentum fusion that we talked about previously. So previously we talked about if you have two spin 1/2, if you want to fuse them, what should be the fusion outcome? So you can see that, for example, the n equals 2 state, which is basically the first excited level, it will correspond to T equals 1/2. But T equals 1/2, we not only have a single 1/2 spin, because we actually have T spin and S spin together, right? So the angular momentum of the electron, the true orbital angular momentum of the electron is actually T plus S. Remember, the T is this one, S is this one, right? If you take T and S, add them together, then that is angular momentum L, basically. So angular momentum is exactly these two more abstract angular momentum T and S, or we can call it T spin and S spin. They don't have a very clear physical meaning, but their addition, their sum, actually has a physical meaning of the angular momentum of the orbital angular momentum of the electron. So if the T quantum number is 1/2, which means both the T spin and S spin are spin 1/2. Remember that there's a relation between T spin and S spin that T squared equals S squared, right? So if T is a spin 1/2 object, and S must also be a spin 1/2 object. So this L will be a total angular momentum that is coming from fusion two spin 1/2 together. We know spin 1/2 particle has two states, plus or minus 1/2. So that means MT or MS can take value of plus or minus 1/2. So when you fuse them together, they are altogether 4 states. And the 4 states can also split into 1 plus 3. Which means previously we learned that if you have spin 1/2, there's a fusion rule. So when T equals 0, 0 tensor 0 goes to 0. T equals 1/2, then it's 1/2 tensor 1/2. That goes to 1. That goes to 0 and 1, which means this basically is n equals 1, and this is n equals 2. And then when n equals 3, that goes T equals 1, then basically you have 1 and 1, and then that fuse into, I think that fuse into 0, 1, and 2, just like that. So we know that when the principal quantum number goes higher and higher, then you have a larger and larger spin, and then the spin is of the same size that has to fuse together and following the angular momentum fusion rule. So we know that the orbital angular momentum that the electron can take goes like when n equals 1, it goes like 0. N equals 2, it goes 0, 1. And you can follow this exercise and keep doing it. If I let me show you another one, and then the rule will be very clear. How do I do 3 half fuse 3 half? Then the angular momentum will range from the difference between these two, right, all the way to the sum of these two, which is 3. And then every time I will add it by 1. So that's why, in this way, the angular momentum that can be taken in this orbital goes like this. So now the rule is very clear. When n equals 1, electron orbital angular momentum can only be 0. N equals 2 can only be 0 to 1. N equals, for any n, the angular momentum will ranging from 0 all the way to n minus 1. Right? That is the rule. So, so that's why the angular momentum quantum number basically takes value from 0 to 2t. And then this 2t is just n minus 1. So then that's a better quantum number because that quantum number has a more clear meaning. And then we can now using this idea of fusion, instead of talking about this, okay, I have t spin and m spin, they range from minus t to t. This doesn't tell us much. But after you fuse these two spins together, so basically, we have t spin and its corresponding quantum number, and m spin, s spin, well, s equals t actually, and the corresponding quantum number. But when you fuse them, it becomes the so-called L and m. So the L and m quantum number in hydrogen atom actually coming from fusing these two spins together. The two spin has the same total angular quantum number, and then the different magnetic quantum number, but diffused into the total angular quantum number and total magnetic quantum number. Okay, so that's why people has these names. These are the names given to the quantum number. N is the principal quantum, called the principal quantum number. It's called principal because energy level is determined by n. N determines the. Remember, energy goes like 1 minus 1 over 2n squared. Like that, right? So that's the only quantum number that sets the energy level. And L is called angular quantum number because it determines the total angular momentum, size of the total angular momentum. And M is called the magnetic quantum number is because it determines, given the total angular momentum, you can still have, that, for example, if you have a non-zero total angular momentum, that means the electron will be orbiting around the nucleus or the proton, then it will create a magnetic field, and then it will respond to the magnetic field. If you really set up a magnetic field, then it will cause splitting of these energy levels. So those splitting are splitting those states with different magnetic quantum numbers. This is because even given the same angular momentum, electron can still orbiting surrounding different directions, right? So if you set up a magnetic field, then certain orbiting direction will have a lower energy. For example, if your orbiting direction is along the magnetic field, it will have lower energy. Against the magnetic field, it will have higher energy and things like that. So basically, so that's why these names are given in this way. So so we basically replaced the original 3 quantum number T, MT, and MS, which naturally arise from solving this SO4 symmetric problem to a new set of quantum number N, L, and M. They are just they're just equivalent set of quantum numbers that label the same set of states. Okay. So the former basis, which is NLM, is more commonly used in atomic orbitals because electron interaction will actually break SO4 symmetry down to SO3. Let me explain this point. When we use this quantum number, we actually make the SO4 symmetry very explicit. SO4 symmetry basically is this T, so-called T spin and S spin that has 2 SU2. SO4 symmetry contains 2 SU2 symmetry. So this quantum number actually labels the quantum number of these 2 SU2 representations. But in more general cases, for hydrogen atom only, and only for hydrogen atom, we have this SO4 symmetry, which is a very large symmetry. But if you consider like a helium atom or carbon atom, atoms which contains more than one electrons, then the potential is not like that. Because if I'm a single electron in a helium, right, I not only see that there is a nucleus that is providing me such a potential background, but there's another electron in the atom. The other electron also carry negative charge, and we try to repel each other. So the electron will see a potential which is deviated from this potential by the electric potential coming from the other electrons. So the potential will no longer take this shape. And the fact that there is a SO4 symmetry is highly related to the fact that the potential shape is precisely like this. If the potential is not like this, for example, if I take this R and put a 1.2 power there, as long as I change I didn't mean that it must be like that. I just mean any change, or if I take any other function, multiply on that, any modification of this potential will basically take you away from the SO4 symmetric point. That's why Mercury actually also orbiting around the sun actually has also this orbital precession. It is because of the effects of other planets, and also because the effect of general relativity. All these factors are changing this potential. The same story happens in atoms. So the electrons, if it circulates around the nucleus with more than one, if there's more than one electron, there's also other electron. It will actually affect each other and then break the SO4 symmetry down to SO3. The system in the end only have a physical SO3, three-dimensional space rotation symmetry. And then the reason that using this quantum number is very good, it is because the angular quantum number and magnetic quantum number is precisely the SO3 quantum numbers. So these levels, these quantum numbers are still good quantum number, meaning that they're still conserved for the hydrogen atom. For the generic atoms, but for hydrogen atoms, these two representations are equally good. But for other atoms, the first representation, NLM, is better. Okay, so that's what I want to talk about this hydrogen atom, and then we can spend a little bit more time on the atomic structure. So given that we know if you have a central potential and then electrons circulating around that, then all the eigenstates will be labeled by these quantum numbers, and then there will be corresponding electron wave function also labeled by these three quantum numbers. These wave functions are also called atomic orbitals, which is the states that the electron can occupy. Electron, I don't want to solve this atomic orbital for you because the idea is still the same. You just need to plug in the corresponding eigenequation, take the Hamiltonian acting on this wave function, and then we already know what are the energy eigenvalue associated with these quantum numbers, right? So we just plug in that energy eigenvalue. By solving the differential equation, one can always find what is the wave function from that. So given the wave function, one can actually also calculate the probability distribution of the electrons surrounding the nucleus. I'm not sure whether this is visible, but I'm trying to draw a picture like this. So this is this picture is in the empty space or black, and then there's a cloud of electron. And maybe if you use your own computer and look at the screen, it's better. Maybe I can turn off this light. Yeah. So this is that okay for? So this is probability. So probability actually can decay in scales, like a probability close to 1 or all the way to probability is very low. And then if you use Mathematica notebook, this is actually you can drag this. You can use your mouse. So I draw 3 axes: red, green, and blue. Red, green, and blue correspond to the x-axis, y-axis, and z-axis. This is the shape of the electron cloud. Associated with which orbital? Associated with this 1s orbital. 1s. maybe I don't need a S1 here, 1s orbital. Yeah. So you can drag it. So you can see it's all spherical symmetric. It's just a spherical cloud. And then you can click on this table. If you click it, it will plot the second orbital for you, and then the second orbital also looks symmetric. But you can see that in the second share, the angular. So in the n equals 1. N equals 1, there's only one possibility for L, that is L equals 1, and M has to be, L equals 0, and M also has to be 0. But N equals 2, there are two possible L. We know that's like 2 spin 1/2. If you fuse, there's a spin singlet state, and then there's a spin triplet state. The spin singlet state has L equals 0. The spin triplet state, or the angular momentum equals 1 state, actually contains 3 states. Which are labeled, which are differentiated by m quantum number equals 0 or plus minus 1. If you look at this L equals 0 state, it's also spherical symmetric. But you can see the only difference is that there's 2 shares basically. There's one share number 1, share number 2. It's like this. You can go to higher principal quantum number, then you will see 3 shares, share number 1, 2, and 3, and so on. But if you go to these p orbital basically look like that. So the pz orbital, the electron cloud, is like a 2 dumbbell shape of things, and then along the z direction, z-axis. But if you go to the, I can try to tilt it. Yeah, it looks like that. Okay, so if you go to py, then it will be along the y direction, which is like that. And then if you go to px, it will goes like this. It will be along the x direction. So you can use this to explore different shape of the orbitals. For example, you can do 3-dimensional. So not 3. N equals 3. N equals 3 is the next, the principal quantum number equals 3, then you will see that not only I have these 2 blobs along the z direction, it actually has 2 shapes, also have 2 shares. So there's an outer share, there's an inner share, something like that. So, so that is that just gives you a more intuitive understanding of what is the shape of the electron cloud. Okay. And there are many pretty shapes, like a D wave, for example. It looks like, for example, DZ square orbital, which looks like there's 2 blobs and there's a ring actually surrounding. Maybe it's not so clear, but if you tilt it, it is clear that there's a ring surrounding that. And then you can also go to DX, DYZ, and things like that. But what I want to explain here is why do people give it this name? So this S wave basically corresponds to, I think I shouldn't write this S1, it's just S wave. So, but S wave basically means that L equals 0, and then the P wave basically means L equals 1, and D wave is L equals 2, and then F wave is L equals 3. I actually don't know why people use these letters to denote this angular momentum, but it is a convention that SPDF, and then next one is G, and then H, and things like that. So, so that's the idea. And then so this orbital P or D basically labels the angular momentum L quantum number. What about this Z, X, and Y? Actually, they are associated with the shape of these orbitals. For example, if you go to the PZ orbital, it really looks like a Z, like a formula that if you write something like Z, then Z is actually 0 along the XY plane and becomes positive along the positive Z direction and become negative along the negative Z direction. So that really describes the shape of this orbital near the origin. So all these letters basically describe the behavior of this wave function near the origin. We don't care what is the shape of the wave function far away from the origin, because the overall shape pretty much determined by how this wave function changes as you move away from the origin. So if the wave function is like a constant surrounding the origin, then that's S wave. And if it goes like a z or x or y, that's just like p wave. But if it is like z square, for example, near the origin, it goes like z square, then it's like that. For example, yz. Yz is like y times z. So y times z, which means this wave function will be 0. The wave function will be 0 if y is 0 or z is 0. So if you look from here, then the green axis is the y-axis, blue axis is the z-axis. When y and z are both 0, y times z are 0. So I'm plotting the wave function squared. So if I didn't plot the square, I plot the wave function value, it should be plus, minus, right? Y times z is plus here, minus here, plus here, minus here. And then the region that this y times z has a non-trivial or high value is along these 4 different directions, and they are 0 along the axis. So that's why this shape of the wave function is called dyz, okay? So that's just the explanation of all these names, and then hopefully that, that helps. Okay? So, so that's the rules. Ln labels the energy shells and controls the radial excitation. If you go to higher n, that means along the radial direction, you have more shells. And L labels this angular quantum orbital angular momentum, which goes like SPDFGH. And then M specifies the orientation of the orbital. Okay.